All right, we're going to dig a little deeper now into change processes, and we're going to introduce a way that we can visualize those processes using pressure volume diagrams or PV diagrams. Let me first talk about a couple of general types of change processes that we're going to be concerned with. Okay, the first of these I'm going to refer to as an irreversible change. Now, what might that be? Well, for example, if I have a container that has a gas in a vacuum, so let's say here's my container that contains a gas, and it's got a valve that I can turn on and off, and it's connected to a chamber that has a vacuum. I think it's pretty obvious that if I open that valve, the gas is going to expand into that chamber, and there's not much I can do about it. It is a fast, spontaneous change, and it is in fact irreversible. Now, I say it's irreversible. We can imagine that the gas isn't all of a sudden going to decide to go from this chamber into which it has expanded back into this bulb and all be there again. No, once it's expanded into there, it's there. So this is why we call them irreversible processes. We're going to be actually concerned a lot with spontaneous processes in a couple of modules, but for now we want to try to get a handle on energy changes that are occurring, and it turns out that these are particularly difficult processes to get that. Now, one of the things that one might indicate, for example, is that if the external pressure outside of a system is greater than the internal pressure, and we open up the possibility of exchanging heat or work, this would result in a compression. In other words, the outside pressure is higher, so it's pressing in on the system. It's going to compress the system. The change in volume is going to be less than zero, so it's going to compress the system. This is a case where work will be performed against the internal pressure. Okay, this is the pressure of reference that we need to care about. If, on the other hand, the external pressure were less than the internal pressure, then the opposite case would happen. We'd have expansion of the system. The change in volume would be greater than zero, and the work would be against the pressure P external. All right. Okay, so these are cases where we've got irreversible expansion or compression happening because of pressure differences between the system and its surroundings. But what would happen if, for example, we had a particular case where the external pressure was equal to the internal pressure? What happens then? Well, we would call this, first of all, an equilibrium. There is no net force that causes a change in either direction. This means that whatever change might happen would happen slowly, and it could be reversed if these things are very close. So we're going to define this as conditions under which it might be possible to have a reversible process. So that's the second type of process that we should worry about, and that is a reversible process. And I'll say right off the bat that this is an artificial arrangement. I mean, there are ways that you can set things up so that change happens very slowly and it's effectively at equilibrium the whole time. But this is not going to be the sort of change that you would see in nature. Nature is going to be an irreversible, spontaneous change. The other thing about this is that for a reversible change, the system remains at equilibrium throughout the change. So this makes it possible to track that change in what's going on. Now, a lot of these reversible systems, we use them in thermodynamics not because they are indicative of exactly what happens in the real world, but because if we can use reversible processes to go from an initial state to a final state and measure a change in a state function, that change in the state function is the same whether the process was reversible or irreversible. So in other words, these are basically describing two different types of paths. Okay, the path could be a reversible path or it could be an irreversible path. But whatever it is, it's a different way of going from an initial state to a final state. And one of those we can actually measure carefully, that is this one. We can measure carefully. The other one may not be possible to measure state functions.